Welcome to the fifth in our space seminar series sponsored by the Colorado Spacecraft Consortium. Today we're honored to have Professor Fran Bagenal with us. Fran earned a degree in physics and geophysics at the University of Lancaster in England, and her PhD from MIT in 1981. She was co-investigator on Voyager, among many other involvements, some of which she'll tell you about, and is currently a professor here at our own Astrophysical, Planetary, and Atmospheric Sciences department over in the Gamow Tower. She's going to talk to us today about the Voyagers, the Voyager missions, and other missions to the outer planets. Thanks. Fran.
Okay, I'm going to start off with what is a fairly nostalgic description of Voyager, and I'm going to concentrate on the program as a whole. We're going to have some pretty pictures, of course, and then I want to talk more about the hard realities, the hard physical realities. Here we are, a few days from what could be utter disaster for space sciences on Monday, 1st of October. And we'll talk about exploring the outer planets of the solar system in those light of those hard physical realities of the 1990s. Okay, so let's go back to 1965, when I suspect a fair number of you had not been born. I had. But back in 1965, a character called Gary Flandreau, who was a graduate student at Caltech at the time, noticed that there's the outer planets, in fact all of the planets in at this period of the late 80s, all the planets would be in one quadrant of the solar system. This is a phenomenon called syzygy, which is a little difficult to spell and extremely useful for Scrabble when you have to get rid of a bunch of Y's, S's and Y's. But what it means is all the planets are pretty much in the same quadrant of the solar system. And you can imagine when you have orbital periods of Neptune of 165 years, that isn't going to happen very often. In fact, that happens roughly once every 170 years or so. And this was noticed by Gary Flandreau in 1965 that this would happen in the 70s and 80s. And that if we could use the gravitational attraction or assistance of these outer planets, we could hop from one to the other. That is, go to Jupiter, get a gravity assist at Jupiter, move on to Saturn, onto Uranus, and then on to Neptune. You'll notice that we cannot fly also to Pluto because, first of all, Pluto is out of the plane. It has a inclined orbit, and also that it is, in fact, at this time, closer to the Sun than Neptune. Pluto's perihelion, a big event here. We had a big celebration here at APAS. Only occurs, his perihelion was in September 5th, 1989, and happens once every 248 years. So the last time that Pluto was this close to the Sun, it was about the time that George Washington was chopping down cherry trees. So I'm told by Americans who know more about these things than I do. Anyway, the point is that it was realized that you could have a grand tour of the outer solar system back in the 60s. And in 1972, Congress approved to pay for a mission. They didn't buy the whole grand tour. They just said, okay, well, you can go to Jupiter and you can go to Saturn. But of course, in the end, the mission was highly successful, and Voyager 2, in fact, went on to all four of the large, giant outer planets. Okay, so I'm going to talk to you a little bit about the whole mission. And let me just, while we're talking about gravity assist, let me just go back a second. You'll notice that those familiar with this business, that to go on this way, you want to go past, you want to pass it on the right as you're coming out from the, if you're coming, you have to go behind it in its orbit to get a kick, to go on, pick up some speed and go on to the next planet, and so on. Whereas Neptune, in fact, was passed over the poles slightly to the left, i.e. ahead of it's in the orbit. Each time you get a kick because you're picking up a little bit of the orbital momentum of the planet. Of course, it's negligible compared with the planet's total momentum. But let me just show you a kind of neat diagram of the velocity of the Voyager spacecraft. This is Voyager 2. It left Earth, slowed down as it climbed out of the gravitational well of the Sun. Then it got a kick when it went past Jupiter. In fact, pulled it above the escape velocity for the solar system. And then every time it went past a planet, Saturn, Uranus, it picked up some more speed. So it kept going at about 20 kilometers a second. But here at Neptune, because it went past on the left, ahead of the orbit, slightly over the poles, it lost a little bit of speed. And then, in fact, went below the ecliptic plane. So that's the sort of flight plan which was conceived in the mid-60s. But there is a good question about why do you have to go to the planets? We sort of take it for granted that you have to go to a planet to do planetary science, because we've sort of got into the habit of doing it. But it's a good question, especially when we're worried about the fact that it costs a lot of money to go to these planets. And you can actually do a lot of planetary science from Earth orbit and from the ground, as planetary science has been carried out. Has that just gone out? Yeah.
The fan hasn't been working.
Oh, well, there's a spare bulb here. Perhaps we could get that fixed. There's a good question of why one should go to the planets, why we should have actually fly by a planet. And there are 4 main reasons that I could come up with. The first is the very obvious one, that if you go close to an object, you get a much closer picture of it, much closer view, and so you can get some nice close-up views, see what's going on, whereas the view from the Earth is very fuzzy, so you get improved imaging. Second reason is that you actually look at the object from a variety of different angles. And when the solar system objects are illuminated by the sun, if you're looking at the objects with different phase angles, you get a lot of information about cold water, I recommend. The 2 other reasons why it's very important to go to the planets. One is that when you pass around behind a planet, you can use this opportunity to do occultations. That is when you measure either radio signals that are diminished when they go through first the atmosphere and then the planet itself, or by looking through the atmosphere back at the sun with, say, a UV spectrophotometer. So you can see the diminution of the sunlight through the atmosphere. And this tells you a lot about the atmospheric structure, composition. The 4th reason is perhaps, in my opinion, the most important, and that is that you can make local measurements. As you will soon find out, I am involved in one of the particles and fields experiments that is involved with making local measurements of the plasma conditions using the Voyager, one of the Voyager instruments. And you cannot measure particles and fields. That's electric magnetic fields and particle fluxes remotely. You have to go there and put your sensor into the medium and sense it that way. So we have to have local measurements, in situ measurements. And when we start looking at the Voyager spacecraft, I'll point out, which are the ones that are making remote sensing imaging measurements and which are making local measurements. Well, let's move on to the slides. Actually, what I had planned. Let's have some slides. Do you think you could turn it on, please? Let me. Do you need to? Okay.
We're getting another projector for you, Fran.
Okay. Great. Thanks. I couldn't resist showing you a launch, a successful launch. And look, an expendable launch vehicle. Do you remember those? This is a Titan Centaur, I believe. I see Larry Esposito is in the audience. Perhaps you can correct me if I make mistakes, Larry. Please correct me if I make mistakes. Of course, this was a long time ago. In fact, I was just a first-year graduate student at the time, just starting at MIT, and I joined the Voyager plasma science team, in fact, about the time of launch in the summer of 1977. So I didn't see the instrument that was put on the spacecraft and sent off, okay? And so there were 2 launches, 1977. The next slide. Oh, I'm going to do the slides. That's all right. I can do it here. Next slide shows you this flight plan that we talked about. Launch of Voyager 2, first in August 1977. Voyager 1 in 1977. Voyager 1, in fact, got to Jupiter faster. Arrived 5th of March, closest approach, 1979. A date that is etched in my brains. And flew then on Voyager 1, then went on to Saturn, took a gravity assist that took it out of the ecliptic plane up to high latitudes. Voyager 2, in the meantime, had a flyby of Jupiter in July 79, then Saturn, August 1980, onto Uranus 1986, just a few days before the Challenger disaster, and then in August 1989 went on to Neptune, taking a gravity assist that took it below the ecliptic plane. Okay. The next is a very dated slide. Oh no, the next one is the one after this. This is a nice picture of the mock-up of the Voyager spacecraft, and this is a life-size scale picture. This is for reference, this is a 12-foot dish. This is the science boom with a lot of the instruments here, imaging, cameras, and so on. These are the infamous RTGs, radioisotope thermonuclear thermoelectric generators. Talk a little bit about those. Keep those well away from the particle detectors. You want to have them other side of the spacecraft. There's a couple of 12-foot radio antennas. Sorry, animals have antennae. The radio antennas. I was told that by a radio scientist. And then there's a 10-meter boom, which is not deployed in this mock-up, which contains the magnetometer instruments, and I'll be talking a bit about those. And then, of course, there's the plaque with the trying to indicate to extraterrestrial beings that there is perhaps intelligent life on Earth, though that's a matter of opinion. Okay, we're going to be talking a lot about the instrumentation. This is just to show this is the magnetometer boom that goes way off over here. RTG's down here. This is sort of backside view. The propellant with the attitude control in here. And a list of the teams. First note, this is the 11 experiments. These are all imaging variety or imaging, or I should say sensing, not imaging, but detectors. Radio science uses the radio transmitter receiver to the signal between the Earth and the spacecraft to do some science. I'll talk a bit about that. Then these are the particles and fields experiments. magnetic fields, variety of energies, particles at variety of energies, and some radio and plasma wave detectors. Now, the list of principal investigators is the original list, and unfortunately, Fred Scarf died of a heart attack about the time of the Phobos over in the Soviet Union, at the time of the Phobos launch. Several other of the investigators have retired. For instance, I believe Rudy Hannell has retired. Herb Bridge has retired. And I think Ed Stone, who's now director of JPL, has probably handed over the CRS instrument pretty much to somebody else. And these have been replaced. The entire teams have had a fair amount of turnover. And, but let me point out, of course, couple of the most important instruments. First of all is the plasma instrument, which is the one which I'm a co-investigator. Of course, this really should be at the top of the list. Then we have another important one, which is Jim Warwick of Radiophysics, Inc. He, in fact, was a professor here at CU. He's just recently retired. And then there is a fairly large contingent of the UV, not the UVS, the photopolarimetry experiment. A lot of people from LASP involved in that. And CU, strong CU involvement. Okay, well, that's a little out of date. Have you any idea how long when this is going to come? Should I?
What?
The overhead. Oh. Is it on its way?
Yes, I think it's on its way. And now to give you the slide.
Okay. Okay. Well, maybe we'll have to.
I'll go check on it. How about that?
Which was I took the slide that you had out.
You did take it?
Yeah.
Okay.
Okay, I'm going to have to reorganize this a little bit because I was going to have some view graphs next. Let's come back and talk about the experiment and the technical details afterwards. And let's just move on. And I'm going to give you a series of slides. And what I've done is, there's a program in England on the radio called Desert Island Discs, where a famous personality is asked to pick their favorite sequences of music, and what would they take if they were deserted on a desert island? What would be the favorite pieces of music? And I've sort of played that game with the Voyager images. I've gone through my selection and I've said which are the ones that really strike me as ones that were either very profound or ones that I thought were particularly aesthetic. Okay, well, we can delay that a little bit. And I think it is important to come back and talk about the instrumentation before we look at the pretty pictures, actually. Okay, right. So let's go back and talk a little bit about the spacecraft. Sorry about this. Can we have the? Yep. Yep, I will. Okay, so here we are, back to the instruments, and here are there's the camera here, wide angle or narrow angle camera, the imaging subsystem, the ultraviolet spectrometer, the infrared spectrometer, radiometer, photopolarimeter here, and then we have these particle experiments, the plasma instrument, cosmic ray, low energy charged particle detector here. They're all here on the science boom. Then we have the sort of housekeeping, if you like, of the spacecraft. And then down here, we have the two antennas that are shared by the planetary radio astronomy and the plasma wave detectors. Really what they are is the same antenna with two electronics boxes attached. And then we have this long magnetometer boom. There are, in fact, 4 magnetometers on Voyager. 2 high-field ones, which are on the spacecraft. But because the spacecraft itself, there are a lot of currents on the spacecraft, generates a fairly strong magnetic field. If you want to measure the very weak magnetic fields, and we're talking fractions of a nanotesla, that's And there are 30,000 nanoteslas on the surface field here on the Earth, if that's some kind of a reference for you. We're talking very weak magnetic fields out in the outer part of the solar system. You have to move them away from the spacecraft, physically remove them from this source of magnetic fields here on the spacecraft. Moreover, it helps to have two magnetometers, one a full 30 feet or so away from the spacecraft and the other one about 15, so you can do a comparison to further remove the effects of the spacecraft field. How does the magnetometer work? It's got coils and stuff. I don't know how it works. You know, I mean, these are complicated magnetometers. I've had it explained to me about 5 times, but I keep forgetting. Look it up in a book. Sorry. This is definitely Friday afternoon. Okay, now you want to get some kind of scale for this, and I thought, how better than to show this lovely picture of Vice President Dan Quayle at the Neptune encounter, and you can see that this is about 6 feet, and so the size of the whole science boom is sort of the size of a human being. Let me just tell you a little about the RTGs. They use radioactive source, plutonium-238, which decays in here, generates particles that then, in fact, produce heat. They go into a blanket, heated up, and then you have a thermocouple across here, and this heat differential, temperature gradient across the canister, if you like, is converted to electricity. And each of these canisters, a canister being about this size, produces about 160 watts at the time of launch. So the 3 of them produce 480 watts. Half-life is something on the order of, I think, 76 years, something like that. So that this is, in fact, dropped now over the 13-year lifetime of the spacecraft a little bit. But there's enough power in these to keep Voyager going until long after we fail to be able to hear it, or for it to be able to sense the Earth, sense the sun to point towards the Earth. Now let me talk a little bit about each of the instruments. These cameras, the imaging cameras, are wide-angle and narrow-angle cameras, produce all those pretty pictures, and I understand the number is something on the order of 75,000 pictures throughout the 13-year lifetime of the spacecraft. And I'm assuming that you're all sort of Voyager junkies, and you've probably read all the magazine articles and watched all the stuff on TV. You may even know a lot more about the spacecraft operations than I do. But you will recognize that as you move out in the outer solar system to objects that are very brightly illuminated at Jupiter, out to Neptune, where the photon flux is down by, solar photon flux is down by a factor of 900, that you will have to have longer and longer exposures as you go out into the outer part of the solar system. And by Uranus, the Voyager engineers had managed to find a way in which they could keep the cameras fixed onto the object and, in fact, move the spacecraft to compensate for the fact that you have long exposures during which the thing that you're trying to photograph will appear to move in your field of view. So by being very clever with maneuvering the spacecraft, they were able to have long exposures and take some phenomenal pictures in the outermost part of the solar system. The PPS instrument is not an imager, but it has a series of filters which look at the various objects. The same objects are viewed, by the way, by all of the target body sensors. And they take it in turns. You know, one might be wanting to look at the planet, the other might be wanting to look at a moon, and so they have to take it in turns to be pointing in the appropriate directions. The photopolarimeter subsystem looks at a range of specific wavelengths, 8 different wavelengths between the UV and the near-infrared. The IRIS instrument is pretty much an imaging instrument. At least it can produce images with very poor spatial resolution, but covers the planet. And of course, the infrared becomes increasingly important as you move out in the solar system, because the objects are getting colder as you move out, and so the black body emission from the planets and from the moons moves into the infrared region.
Fran?
Yes?
A photopolarimeter, am I remembering it well? Is that what was used to look at the rings?
Yes, that's a good point. You can, the way the rings of all the planets were imaged was using the camera, but in addition, at Saturn, Uranus, and Neptune, there were some opportunities to use the photopolarimeter in a very clever way to do some occultations of the rings. And the way this works is that you look at a star that moves behind the rings. Okay? So you track on a star that moves behind the rings, and the motion of the spacecraft sort of brings the star across a cross-section of the rings. And so monitoring the intensity of radiation from the star through the rings, you can measure the absorption or the scattering of the light from the star by the rings. And the PPS instrument had very high time resolution, didn't make an image, didn't have spatial resolution, but it had high time resolution. So as the star tracked through the rings, you get a very detailed map of the variation in the intensity of the star through the rings. And so you can measure very small structures in the ring system, and not only measure the size, but also the depth of the absorption, the amount of material that was there absorbing the starlight. And Larry Esposito has been and his colleagues at LASP have been using this to great advantage to study the rings, ring structures and dynamics. Okay, I should move on to the UVS instrument that measures, in fact, the far UV, extreme UV, and far UV, and it was very important for looking at the atmospheres. That was its original design, but it also was very important for a lot of aeronomy, a lot of upper atmospheric science. And the most important thing is to look at the eoplasma torus, which is what I studied for my thesis, and I'll talk a lot more about it, of course. Made very important measurements of the eoplasma torus. So we'll come back to that. Now, let's get on with the particles and fields instruments. These ones here, the plasma science, low energy particles, and the cosmic ray subsystems, all are particle detectors that measure particles, both positive and negative particles, in the range of EV, few EV to 1,000 EV, several thousands of EV, and here MeV. So these are sort of separated by 3 orders of magnitude, if you like, between each one, and they go from 1 EV, 10 electron volts, up to million electron volt energies. The plasma detector is in fact a variation on a Faraday cup using grids to retard charged particles coming in a retarding grid, and then a collector plate, essentially measuring a current, a flux of charged particles with the particular energy, those that have enough energy to get through the potential of the grid. And the currents are measured in femtoamps, thousands of femtoamps. That's 10 to the minus 15 amps. So we're not counting particles, we're measuring a current, but it's a pretty small current. These other particle detectors are solid-state detectors that have particles penetrate through, and they have various thicknesses of material to try and stop the energetic particles coming through. And then they count the ones that manage to get through various layers of shielding material. So these these measure the more energetic, and these are called low-energy charged particles, which is a sort of low energy, is very relative. You know, we always regard them as the more energetic ones, but if you're a cosmic ray scientist, you'd say it was very low. So it's a relative matter, but it's kiloelectric electron volts. The magnetometer instrument I've mentioned with the 4 different instruments, 2 on the spacecraft, 2 on the booms. And then we have the radio astronomy and the plasma wave instrument. And both of them are really measuring electric fields at different ranges of different frequencies. And then the radio science instrument that uses the radio signal between the spacecraft and the receivers on the ground to do some science. And particularly, they do two particularly important things. One was the tracking of the spacecraft itself as it went past a body to measure big G times the mass of the object that you're flying past. And so you could get a very accurate measurement of the mass not only of the giant planets themselves, but also of smaller objects such as Titan and Triton and Io, the moons, the larger moons. So you're using the spacecraft, if you like, as a test particle in a gravitational field. Okay, well, there was a lot of publicity and a lot of excitement. I've received, in fact, a large collection of press material just from the Neptune encounter. JPL did press cuttings and put them all together on it. You know, about 1.5 inches of copies of articles that came out in all sorts of journals across the world. I've just shown the French example. Clearly, Voyager was a highly successful mission that not only demonstrates enormous skill for the engineers, and indeed they performed wonders, understanding various malfunctions and then finding ways to correct them, compensate for them. But this has had an incredible boon to science, and planetary science in particular. So let's just have a little nostalgic trip through the slides. If you could turn the slide projector on, please. Excuse me, could you turn the slide projector on? Thank you. Start off, could we actually have with spectacular picture taken by Voyager of the first picture really of the Earth system, the Earth Moon here together, as Voyager moved away from the Earth out towards Jupiter. This is a ground-based picture of Jupiter, and just to give you some comparison with the Pioneer picture to the right and the Voyager picture to the left. And so the improved camera on Voyager clearly produced much better resolution, spatial resolution. And I've showed some of my favorite pictures. This is the picture of Jupiter with the 2 Galilean satellites, Io and Europa. And this was taken as we were coming up on these satellites, really not knowing just how extraordinary they would turn out to be. This is my favorite picture of the clouds of Jupiter, the big red spot, and all the neat clouds. I have a copy of the movie of the cloud picture and show it in my astronomy classes. It never ceases to amaze me how fascinating these cloud structures. Neat stuff going on. This is a composite of the pole. I forget which pole. One of the poles of Jupiter. I guess it must be the northern pole. And you can see this incredibly circular structure strongly dominated by the rotation of the planet, strongly controls the dynamics. But then there are these sort of cumulus convective clouds coming up, these sort of dark spots of presumably gunk brown clouds, the equivalent of the brown cloud around Denver, but out at Jupiter, same sort of thing, probably photochemistry on sulfur compounds. The trouble is we don't actually know what the atmosphere is made out of, and we'll come back to that issue a little bit later. This is visible. This is just the imaging pictures of Jupiter. Another famous picture at Jupiter is the discovery, associated with the discovery of volcanoes on Io. One of the nav team was trying to fit circles to the satellite to try and help with the navigation, and found that there was a very high residual. And when they looked at the picture, they found that there was some material being ejected off the side. And this was the discovery of volcanic activity on Io. This is one of the big volcanoes, Pele, which is, I think, comparable to the Hawaii Mauna Kea. Is that right, Larry? In size? Sorry?
It's a couple hundred.
Couple hundred kilometers across. Okay, so that gives you an idea of the size. Yeah, it depends how you measure, where you measure the base from. Okay, so this is a large volcano producing a lot of material, and it was clear when you look at the surface of Io, you can't find an impact crater anywhere. And so clearly this surface has been reworked, and Io is perhaps the most, in fact, certainly is the most geologically active object in the solar system. The surface being recovered very rapidly. And what is this stuff? Well, a lot of it is associated with sulfur compounds. The white stuff is probably sulfur dioxide frost. And there are some other structures that look more like rocky mountains. And this whole business of the geology of Io has been keeping a lot of people very busy and excited and interested. There's a whole science on Io. I mean, I could just talk for about 3 lectures just on Io and science associated with the Voyager discoveries around Io. But this is a sort of composite picture of the back and the front, and you can see the whole surface is pockmarked with these things. They're not uniformly located. There are some differences. There's different kinds of volcanoes, different kinds of plumes. I'm not going to go into the science. It's fascinating and exciting. I'll just show you the pretty pictures. But we'll come back to Io when we're talking about the magnetosphere and the plasma size. This is a picture of Europa. The close-up pictures taken by Voyager were not very close, but it's a remarkable. It seems to have a remarkable surface, very, very smooth, and appears to have these scratches like a cat has just seemed to have scratched this ice ball. And it's thought that there's a very thin layer of ice over an ocean of water, and it's smooth because the thickness of the ice can't sustain a lot of relief. You look up close, you see these cracks, a bit like an eggshell that's been cracked all over. The Voyager pictures were frustrating in that we didn't get very close, couldn't get a lot of, the resolution is not very good. Galileo will go back and take a lot of good pictures, and this is a major target for the Galileo spacecraft. Ganymede, one of my favorite pictures of this strange, mixed up satellite that seems to have all sorts of sort of areas of dark ice, areas of fresh ice, impact craters where fresh water has been spewed out and then frozen. And then when you look close on the surface, there's some very weird terrain. It looks as if some off-terrain vehicle has been running all over this place, producing this. And I know a lot of planetary geologists have been studying, working out what they believe is going on. I haven't, I'm afraid, been keeping up with all that. But I suspect Galileo, again, will help us a lot. This is a close-up picture, and you can see there are blocks of dark ice and blocks of light ice, suggesting that we've had if you think of it as being ice flows, like the Arctic ice flows, it's been broken up and then refrozen. And then impact craters have come on top, splashing out fresh ice. And then there's been these vehicles that have come all over and...
Is it the infrared spectroscopy that tells us that it's water?
I think the ground-based spectroscopy will tell you that it's water. The density will also give you a clue that this is a mixture of rock and ice, this satellite. And then Ganymede, the outermost of the 4 Galilean satellites. Callisto, outermost of the 4 satellites, which you can see is completely covered with impact craters. So here we have a contrast between the innermost of the 4 Galilean satellites, Io, which has no evidence of impact craters, very recent active geology, and here we have Callisto that is totally covered, saturated, so that if you came in with another impact crater, the probability is 1 that you would hit another impact crater. You'd have to cover up something else, another impact crater. So it's a completely covered surface. So therefore, it must have been, this surface has not geologically active. It's not being reworked. Okay, I mean, I know that I'm not really saying much about the science. I just really want to show you some of my pretty pictures. This is a picture of Saturn taken from the ground. And I'll tell you, though I won't tell you how. I've seen a picture from HST, and it's better than this. Here you can see the Cassini division. It was discovered by Cassini. The rings, beautiful. Not much evidence in the atmosphere. And then Voyager went in, and you can see. In fact, the HST picture is probably about comparable to this in terms of quality. Here now you can see a lot more. You can see the Encke division. It doesn't show up very well in this particular picture, sort of chopped off at the edge. You can see a lot more structure in the rings, and you can begin to see some structure in the atmosphere.
Those are moons?
I believe so, though I couldn't tell you which ones are which. I would guess. Well, I better not guess. That's silly. Okay, this is a picture from the atmosphere of Saturn is a lot less dramatic than the atmosphere of Jupiter, or appears to be. That's because we actually have to look a lot deeper in the atmosphere to see these clouds, and the cloud layers are more separated apart. But just look at this for fluid dynamics. There's some really exciting stuff going on here. There's a lot of interesting things to look at. And a point that I'll come back to later, not a lot is being done with the Voyager data set at Jupiter and Saturn. I just want to show you a composite picture that was given to me by a friend, a British friend who's been studying these images of Saturn. I don't want you to concentrate on the peace sign. I want you to look, which is between the images, but to look at this structure here. And this has 1, 2, 3, 4, 5, 6 sides, a hexagon in the polar atmosphere of Saturn. And a recent result that is recently published, I believe, in Nature or Science, I forget which. David Godfrey shows that this hexagon rotates with exactly the same rotation rate as the magnetic field of Saturn. And the magnetic field is believed to be generated in the lower region of electrically conducting hydrogen in the inner region of Saturn. So this pattern is not dominated by some wind pattern. It's dominated by some deep, some connection to what's going on deep lower down, which is an exciting new result. I should point out, when this was first found, people said, how can you produce hexagons in the polar flow? And then in the studies that were being done of the ozone hole and the flow around the poles of the Earth, the numerical simulators said, oh, no problem. You want a hexagon, you want a pentagon, you want a heptagon, we can generate it, no problem. And so there's some interesting studies about rotation-dominated flow around poles, and believe it or not, this is connected to the ozone problem. Scientifically, not human involvement. Now we move on to the rings. I thought this was a remarkable picture. It really shows how thin and transparent these rings are. This is an opportunity to point out this is a sort of view that you cannot get from the Earth. You have to fly by the planet to take this picture where you look through the rings. Here's the terminator on the side here. And here's the shadow of the rings on the planet. And this shadow interferes with the wind structure up here, because there seems to be a very strong winds here at the equatorial region, much stronger than any other planet in the solar system. I'm not going to say anything more about the rings. Again, Larry could probably lecture give a whole course on the rings. In fact, he does give a course we should probably encourage you to take on rings and planets in the APAS department. But again, look at this parting shot of Saturn, and you can see the shadow of the planet and the rings. You can see the variation in opacity of the rings here. Again, this picture could not be taken from anything other than a flyby. Of course, as the spacecraft then swung further around, you can look through the atmosphere, either look at the sun and use your UV spectrometer to look at the constituents of the atmosphere, or you can use the radio signal to sound the pressure versus depth as the signal changes as the planet comes in front of between the spacecraft and the Earth. Now, if we move on to Uranus, not really very exciting. I just want to show this one picture of the cloud, which goes from here, moves over to here, moves over to here and here. You can see that there's really not much to see on Uranus. Unfortunately, in terms of pictures, the atmospheric dynamics is in fact very puzzling, big question. You would expect that a planet that has its rotation axis pointed towards the sun, so you have very extreme summer on one side and then very extreme winter on the other, the orbital period or the season being 84 years, annual season, you would expect it to be very hot on this side and very cold on the other. But in fact, it turns out that the temperature appears to be, each side seems to have similar sort of temperatures. So there's something very strange going on with atmospheric dynamics at Uranus, but nothing very spectacular to look at. This is one of the many moons that were explored by Voyager. This is little Miranda, the size of Texas. It's 300 kilometers across. And it's believed that this object is the result of a major impact of a larger moon, that the material, the debris, then sort of stuck back together in some sort of hodgepodge way. And so you have different bits that were produced when a differentiated planet, a satellite that was large enough to have a rocky inner bit and then a less rocky outer bit and ice on the outside, could get bashed up and then these different bits put back together. And so this has a very sort of strange geological appearance. And my favorite picture from Uranus is in fact this picture, and those of you who are rock climbers like me will look at this and say, this is El Cap. And in fact, it turns out this looks just like El Cap to me. This is about 20 kilometers high. And because Mimas is only 300 kilometers across, you can start at the bottom and this is ice, right? Get your ice tool and put it in the bottom, and then you jump, and you'd be near the top, the second one. You'd be just leaps and bounds up this 20-kilometer high face here. So I want to go out to Uranus and go ice climbing. The Uranian rings, first discovered by stellar occultation from the ground, not from the ground, from the airborne observatory around an aeroplane in the Earth, from the Earth. Very dark, very thin, like thin linguini around Uranus, but very tightly confined, and in order to be so tightly confined, you would expect them to spread out over a period of time, just due to the particles colliding and diffusing and spreading out. But there must be some means of confining them, and the explanation of these very narrow rings that has come out is that there have to be larger moons that are sort of acting like sheepdogs or shepherding moons, holding in the gravitationally holding in the particles that make up the rings. Some of these potential shepherd satellites have been observed, but nothing like as many as you would need to shepherd all these rings. But there is, in fact, a gap in the observational. They may be smaller than the observational limit. So there's a lot of exciting stuff associated with rings. Remember that at the time of Voyager launch, these rings were actually discovered the same year as the Voyager launch. But just before this discovery, it was thought that Saturn was the only planet that had rings, and Voyager discovered rings around Jupiter, explored the rings of Saturn and Uranus, and discovered rings around Neptune. So rings are now ubiquitous in the outer part of the solar system. This is a picture which, when this came up on the screen during a science meeting of the Uranus encounter, we thought, wait a minute, they've just thrown a picture of Saturn up by mistake. But it turns out that this is a picture taken when Voyager went the other side of the rings, and this is forward scattered light. So we're not looking at the reflection from the rings. This is forward scattered light, and this means this forward scattered light comes from dust particles, minute dust particles. And this perspective, and hence understanding that the rings are not just the thin linguini, but also comprise a dust cloud, could not be obtained from any from the ground or from any occultation, stellar occultations. You have to fly by and get a look at these rings from a different direction. This is a ground-based picture taken by Heidi Hamel from on Hawaii of Neptune, sort of fuzzy ball. This is the best you can do with the best instrumentation and the best luck with seeing from the ground. You fly by and you get this beautiful picture of Neptune with a dark spot, nice, sort of very laminar looking flow, unlike the turbulent flow at Jupiter. I don't know what, yes?
Almost like a spot in the lower.
This spot here? Yeah, another spot here. There are actually several spots, but this is the eye, that one's called. That's my...
Is it anything like the real color?
Well, real color. Oh, yes, that's a difficult question. Of course, it's hard to know what is real color. I mean, what is real color? That's a whole, what do you perceive to be color, and so on and so forth. The pictures are taken with 3 colors, and they're put together to make some idea of 3 filters to give you some idea of color. And you can fiddle a color balance. This is probably somewhat enhanced to make it a little blue and make it a little more exciting than it really is. It's probably a little less blue than this. But I have been showing you true rather than the false color pictures that are gross exaggerations that are used for publicity purposes, which drive me crazy. You know, my students think that Saturn is orange and green and purple because those are the colors that they see in the magazines. Okay, then we move on to Triton, which appears to be one of the large moon of Neptune, which has all sorts of very strange geological features, including what is famously known as the Cantaloupe terrain, and some icy structures here, and some what are now known to be volcanic vents here, these sort of black streaks here. Triton is another one of those objects in the solar system that has all sorts of exciting things associated, all sorts of geology. But the reason why I want to put this up here is that to tell you that with 9 pictures of Triton, we completely revolutionized the science and the study of this object. Just 9 pictures. And Pluto is about the same size as Triton. about the same distance from the sun. And what would we give to have 9 pictures of Pluto? I can tell you, it would be fascinating to compare with Triton. That's going to come back to that one if we have time. Finally, the rings around Neptune, discovered by Voyager. And then the family portrait of the 4 giant planets as discovered, as explored by Voyager, completely changing our understanding of the giant planets and the outer solar system. Point I should make here is that this incredible quantity of data obtained at particularly Jupiter and Saturn, where there were high data rates with closer into the Earth, which has barely been, it's been touched, we've worked on it, but there's so much more there that hasn't really been explored. Now let me just tell you a little bit about the particles and fields experiments. The magnetosphere of Jupiter, the largest object in the solar system. This is 1,000 times the volume of the sun. Huge object. A region dominated by the magnetic field of Jupiter. The solar wind again streaming in front because it's supersonic. You have a bow shock. And behind you have a region that is controlled by this magnetic field of Jupiter. Inside the magnetic field of Jupiter, we have the Galilean satellites, in particular Io with its volcanoes churns out sulfur dioxide. The sulfur dioxide becomes ionized, and you get a large torus of ionized material, sulfur and oxygen ions and electrons, that is carried by the magnetic field and rotates with a 10-hour rotation period, swept around in this donut. Voyager flew through this cloud. Plasma measurements were made, magnetic field measurements were made. I wrote my thesis on the analysis of the plasma measurements that were made. We can now monitor activity from the ground using optical astronomy, the emission lines of sulfur and oxygen lines, sulfur and oxygen ions, and we can monitor it using UV spectroscopy. I normally use this slide as the basis of an entire talk, talking about the interaction of Io with the magnetic field and the material around it, the currents that are generated by Io generating radio emission, the aurora that's produced when energetic particles stream in to the atmosphere of Jupiter. We're currently going to have an observing program to look for X-rays using the ROSAT spacecraft next year, looking for X-rays from the aurora, looking for UV emission from the aurora, and optical emission and UV infrared observations. All these sort of things can be done now from the ground and Earth orbit, monitoring and trying to understand the activity, the interaction between Io and the magnetic field and the plasma. But we didn't have a clue of this, or a few scant clues before the Voyager encounter. But after the Voyager encounter, we can do a lot of science, a lot of monitoring, a lot of investigation of time variable phenomena from the ground and from Earth orbit. Magnetosphere of Saturn, relatively boring compared with that of Jupiter, but again inside you have embedded satellites, and most of the material comes from the interaction of the satellites with the plasma. At Uranus, we have a very interesting situation. The rotation axis is pointed towards the sun, but the magnetic field axis, instead of being pretty much aligned with the rotation axis, is tilted by about 50 degrees away. This produces a very interesting structure in the magnetosphere that varies with as the planet rotates. I have some models here with magnetic fields, and we can talk about that afterwards. I don't have time to go into it now. We thought Uranus was strange because it was tilted on its side, and so it has a weird magnetic field. But of course, we expected Neptune to comply with our expectations and have a aligned dipole. Of course, when we got there, we were wrong yet again, as we've been wrong at every single planet that we've discovered a magnetic field. The rotation axis is here at Neptune, but the magnetic field axis is tilted again by 60 degrees. And so we have a very strange situation that at one point in its rotation, the magnetic field looks like this, and we have a magnetosphere that looks pretty much like that of the Earth, but half a rotation period later, we find that the magnetic axis is pointing right into the solar wind, and we have a very strange configuration, which is changing every rotation period. Okay, well, if we could have the lights back on, please. What do we do now after Voyager? Is there life after Voyager? And many of us who'd spent 12 years working on Voyager data wondered if there was life after Voyager. And the answer is yes, of course there is. There's lots of interesting things we can do. Perhaps the most important thing is to look at what Voyager did not do. It did not visit Pluto and the Pluto-Charon system. It didn't visit Charon, this exciting comet asteroid, the outer solar system. It didn't visit the Trojan asteroids. It didn't stay and monitor the environment around the giant planets. It just took a snapshot. It didn't probe the atmospheres. It just flew by. We don't really know what the composition is of the atmospheres and what makes, particularly, we don't know why. What's the red stuff in Jupiter's and Saturn's atmospheres? When we didn't map the magnetospheres, we just flew through once each time. And so there's a lot of important things to do in the outer solar system. One spacecraft that's going to help us with this is Galileo. Have the slides back on for a second. Galileo was launched last year. Spacecraft that is going to go out and put a probe into the atmosphere named after the discoverer of the Galilean satellites. This is the spacecraft being tested out, went through a variety of incarnations. It was originally supposed to be launched in the early 80s. It was finally launched in the late 1989. So it's finally on its way. It has to be wrapped up because it has to go past Venus before, and then past the Earth twice before it gets out to Jupiter in 1996, when it will drop a probe into the atmosphere, and finally we will understand about the lightning and the clouds, the atmospheric constituents, and then the spacecraft will orbit around, looking at all the Galilean satellites, taking many pictures, and mapping out the entire magnetosphere. And so we will have many pictures of the Galilean system, the Jupiter system taken by Galileo. The instrumentation is very similar to that of Jupiter. It's about the same size as Voyager. It's about the same size as Voyager. It will, of course, be considerably more expensive than Voyager. And that gets me to my final point. I'd like to talk a lot more about possibilities of exploring the outer solar system. But the important point I want you to come away from this seminar is that Voyager was a unique opportunity to go to these giant planets because of the alignment. But secondly, we will never have another Voyager, not just because of that alignment, but because it was a huge, big, expensive project. These projects get bigger and bigger and more expensive every time. It's not that we aren't capable technically of doing these things, but we're going to have to face some very real financial issues in the next decade or more. Okay? So these grandiose ideas of going to comets, getting material, bringing it back, flying and having orbiters around all the outer planets is just a dream that I'm afraid is not going to happen in our lifetime. And what we have to do is completely change, get away from Voyager, forget Voyager, not because it was bad, of course it was glorious, but to think about ways of going to the outer solar system cheaply. And there are many ways in which you can do this. You're not going to have 11 instruments. You're not going to have the data-taking capability of Voyager. But remember those 9 pictures of Triton that completely changed our view and gave us an incredible amount of information about Triton, that one object in the outer solar system. And what I just wanted to throw up a picture here of how we can use going to Jupiter to do a variety of things. One is to go to this object Chiron, very interesting object. One is to go to Uranus, and go to Uranus when it's at a different alignment. I'll just show you that in a second. And another is to go to Pluto. We must go to Pluto, and we have to do it in 2002 because we have to go past Jupiter, and it doesn't. That only happens once every 12 years. And we have to get there before about 2015, when the atmosphere of Pluto will collapse, because Pluto will then be moving away from the sun. Its tenuous atmosphere will collapse, and that will freeze out to form frost and ice, and that atmosphere will not regenerate for hundreds of years, more than 100 years. Because remember, we have an orbital period of 248 years. This won't happen for another 3 generations. So we have to do it, and we have to do it soon. However, there's the political problem of trying to sell a mission that will have a 14-year cruise, will not return information for 14 years, and when it does, it'll be a half-hour flyby with a handful of pictures. So you can't have an $865 million project, such as Voyager, with 11 instruments and so on and so forth. We have to send out just a camera and maybe a UV instrument and a plasma instrument. 3 instruments. Cut back our scientific desires to have more, and just send it out and take those 10 pictures before the atmosphere collapses and we lose the chance for 3 generations. But there's an enormous reluctance in NASA, at the Office of Space Science and Applications, and amongst a lot of scientists and the engineers at JPL and other places, to think about small missions, sending gas can type instruments out to the outer solar system. The scientific returns are enormous, but we have to completely change attitudes towards risk-taking, towards systems, towards the whole planetary exploration business. Well, I'm sorry I've run way over time, but that's it. Thank you.